In this session, we're going to have a quick look at the task of configuration management and how you can achieve that using RDFox. This is loosely based around a use case we have with one of our clients. However, none of the data you see here, nor the rules, or in fact any of the assets we're using here are taken from that particular engagement. All it really took was inspiration from that particular application. For today's session, we're going to be looking at the art of configuration management. There's a bit of a demo. There's a RDFox project, and the demo itself composes of a small user interface we've built to really illustrate the point and show an interface or the basics, the rudimentaries of an interface you might have with one of your applications or clients. In essence, the task we're trying to solve is to look at assemblies of components, and those assemblies are going to have some sort of criteria that you might want to search for on those assemblies. And here in particular, we're going to be looking at rotating assemblies and asking questions such as, give me an assembly of components that can spin at 2000 RPMs and provide a particular amount of torque at the end of that. So something you might want to use on a particular assembly line or as part of some sort of machinery that you're trying to construct. As we said, the session is going to include a fair amount of demo to show you how this all fits together. So why don't we switch over to that straight away? What I'm showing on this screen is an interface that is the interface we built for this particular demo. So I'll show you the end result, and as we go through the presentation, we'll then unpick the details of this and show how it was constructed. So in essence, as I said, we're looking for these configurations of possible components. Configurations might be power supplies, motors, switches, and so on. And ultimately, those need to deliver a set of results. So let's start typing in some of the criteria that we want to search the possible configurations that are within our solution. I'm going to put in a speed of 800, torque of 2000, and you see as I'm typing, in fact, as I type particular digits into my search, the results are refreshed almost immediately on the right-hand side. I can search on speed, torque, and also later on we might want to add in a cost element. And over on the main screen, we see both the number of solutions that our criteria reduces the set to, along with a sampling, in fact, the first page of results that meet our criteria. And for convenience, those have been ordered on cost. Finally, if I was to click on one of these components, we see how this particular configuration has been assembled. So it's an assembly of, if I start from the bottom, a power supply. So here we see a DC power supply. It's then using a brushless motor. So the brushless motor needs a brushless motor controller that powers the brushless motor. And finally, we've got an 11-to-1 gearing. Each of the items has a cost, and those costs obviously together are aggregated into my overall cost. The idea here would be if the client is comfortable and wants to proceed with this particular configuration, then they might proceed to purchase that. So there's, if you like, the end result that we're aiming for. So that gives an idea of where we're heading for. Now let's just unpick a little bit. And in fact, I haven't really explained the whole concept of what a configuration might be. So I'm going to use a presentation to illustrate that and go through some of the details. So if I flip back to our presentation, we can go through that. First off, I'll just present the problem itself. Configuration is a challenge. Configuration for these types of machines requires checking potentially millions of combinations to see if the components you're trying to put together, so in the demo we saw a motor, perhaps a particular type of motor, stepper motor, its controller, its power supply, and so on, to see if they all fit together, and that's both physically, but also there are going to be other constraints on compatibility. Things like batteries and motors, they need to be set to the same voltage, might have controls over the current they draw, and so on. And then we've got specific requirements for our overall configuration. We were looking for how much torque, how much speed the configuration as a rule provides. Okay, so there's the challenge. And an example, I made reference during the introduction to one of our customers, manufactures and assembles components for industrial automation. Their configurations, rather than these rotating components, are moving components perhaps on a factory floor. They have or have had in the past somewhere of the order of 30,000 components of axes, motors, gears, and controllers. So imagine the process of trying to work out all of the possible combinations of those components to make sure you're best representing the possibilities that are available to your clients. This is how one might have solved this in a traditional SQL style manner. So in a database, in a relational database, you would have all of those components, the axes, the gears, motors, and so on, loaded into a set of tables and perform a series of join operations on those tables to establish where compatibility existed. And you end up then with a complete system that shows the full possible configurations and combinations. This is how this problem has been solved in the past. And this is just the realization of those joins, making visible the views that integrated all those components. That used to take of the order of hours, in fact, a little over half a day in this particular example. So that poses a number of challenges. One is if the system changes, you have a long iteration cycle in which to see if the changes you've made are actually viable, compatible, and fit into the overall system. This hinders also checking for correctness, for consistency, because of that overall long cycle that you have to go through every time you make a change. Overall, you have resistance to change within such a system. So here I present a number of the reasons why we think RDFox is ideal for this solution. It's in memory, it's quick, actually extremely quick in this particular application. It has reasoning capabilities that are really well suited to this particular application. We'll see those as we go through the demonstration itself. Flexibility with incremental aggregation for addition and retraction of data. What does that mean in practical applications here? It means if I add a component, if I withdraw a component, all of the consequences of that addition or retraction are automatically calculated for me by the system. I don't need to go and rerun a long 15-hour batch process, for example, to see those changes. And it's built for speed and parallel materialization, and we'll see the benefits of that as we go through. So first off, we need to model the data, whereas SQL would have had to have very specific tables to model out schema for the particular types of components we had and how to establish the compatibilities. In RDFox, we get to use a graph to model. So we have ultimate flexibility in how we both model that data, how we think about it, how we conceptualize it, and ultimately that's going to lead to improved data quality. Now, worth mentioning at this point, when the particular customer we reference was looking into a switch to a graph-based technology, they did explore others, and RDFox was by far the fastest and most correct of the solutions that they evaluated. So let's turn now to the particular application that we've mocked up, that we're demonstrating today, and think about some of the components we have in there. The most simplest assembly we might have to create one of these overall rotating assembly of components is one with a motor. A motor provides obviously the end rotation in this case. Motor requires a power supply, and a power supply may require a switch. For each of these, we can think about breaking that down a little bit further. So that's a motor providing both the rotation, the speed, the torque. Remember, those are some of the criteria we're going to search for our configurations. And a motor requires a power supply. That power supply needs to satisfy certain conditions, a voltage, a current. So that's provided by a power supply. And a power supply in our example requires a switch, and the switch must be rated for a particular voltage. So you can kind of see how some of this is coming together. So let's then think about not just these three examples of components, but let's think about the full set and range of possible components. Well, again, RDFox and semantic technologies comes to the fore here as well, because as well as thinking about a motor as perhaps a particular type of motor, such as a DC motor, a stepper motor, or a brushless motor, we can also have concepts such as those being subclasses of a higher order concept, a motor. Gearing we can think of as well. In fact, both gearing and motors, we can think of those as subclasses of overall rotating components. So we can build up these rich hierarchies that we are going to then use to both encode our system, but also take advantage of when it comes to querying the system. So now, for example, if I don't really care which type of motor's used, I just think I need a motor with a particular criteria, then I might use the subclass relationship and abstract out all motors, the three types of motors shown here, to the concept of the superclass, the motor class. and so on and so on. So hierarchies are really useful and can be brought to bear on these types of applications. Right, now let's then drill into a particular instance of a motor. So this here shows a particular DC, direct current motor. So it's going to be, just relating this back to the previous hierarchy chart, it's going to be of type DC motor. This is a specific instance. This provides rotation, it provides 2000 RPM, and it provides a particular torque, but it also has some requirements. It requires a DC voltage, it's a DC motor. It requires 12 volt as a fixed amount, and it requires a power supply that's going to supply at least 2 amps. Okay, so that's for the attributes of a particular component. What we might want to think is then how are its requirements satisfied, and constraints, if you like, allow us to think about that as well. So here's again an instance of a power supply, and here we're showing what that power supply provides. So again, it now provides a DC voltage, it provides 12 volts, and it provides 4 amps. And our constraint in this particular case, thinking back to our knowledge of electronics, the voltage requirements and provision need to match identically, whereas for the current, the power supply must supply at least the amount of current required by the motor. So 4 amps is greater than 2 amps. This power supply is a compatible match for this particular motor. So we're going to use this to define relationships between now each instance of a DC motor that is satisfied by the constraints of power supplies. And every time we see that, we're going to be using RDFox, and specifically rules within RDFox, to establish new relationships not present in the input data, but the realization of the input data, the requirements, the provisions, and establish compatibilities between those two compatible components. Okay, with these compatible relationships, we can then think about a bigger picture of many different components with different requirements, different provision, and how that then draws out against a graph. And here I'm just showing an illustration of a subset of an overall graph. We see lines that you could follow between a gear, a motor, a power supply, and a switch, or in some cases where you've just got a motor, power supply, and a switch. In some cases, let's take stepper motors or brushless motors, they require some form of controller, so slightly different configuration. The graph here illustrates all the different combinations that might exist within the thousands of components that are present within our system. To reiterate, if you follow one of these green lines, of the green arrows, those individual lines or sequence each represent one possible configuration of the system where all the components of that chain form a compatible solution. Again, so if we took one of those lines, we now have the endpoint we're kind of looking for. We have possible compatible set of components, each together compose themselves into an overall rotating solution. That's determined when each of these items are matched by one of these compatible with relationships. And for each of those, we're going to use, again, rules to determine these possible assemblies and assign them to a new rotating solution. And that rotating solution, by again doing the maths on each of these components, will in turn provide a rotation of a particular speed and a particular torque. Okay, so let's have a look at how this was constructed. Well, we had some initial data, all of the components, their attributes and their constraints. And this was our input data to the system. I'll show you an example of that in a second. And the form that took was RDF turtle files input as data, input as triples into RDFox. Second piece of the puzzle are the rules, the definitions of compatibility. So how a motor is compatible with its power supply, for example, and also valid configurations, the fact that you can have a motor plus a power supply plus a switch, and that is a valid combination for a rotating solution. An alternative solution might be a stepper motor plus a stepper motor controller plus a power supply, again, a valid configuration, and so on and so on. So each of those are represented by rules within our system. The output are these rotating solutions. So rotating solutions not present within our input, but derived from the combination of data and rules. And the rotating solutions are what we're going to query on. When I showed you the website, the small mock-up website application, that was issuing queries against RDFox for these rotating solutions. And we'll go into the details of that as well. Okay, so here's some sample input data. I'm showing you the example we saw earlier, and we have the illustration on the right-hand side, and over on the left in our box here, we see how that was actually specified using Turtle in an input file for RDFox. So a DC motor has an identifier, has a name, it has a cost, and then all of the things that it provides and all of the things that it requires. And it's as simple as that. So all of the requirements can be laid out nice and elegantly within our RDF file. And if at this point I switch over to Visual Studio Code, which I'm using as my editor here, we can see examples of DC motors. I can scroll through and we can see examples of some of the other motors within our system as well. Some switches, some power supplies, and so on and so on. We move now into the brushless motors, and you get the idea. Down in my terminal, we see that RDFox is running. In fact, I already have it running, so that we saw our demo live earlier. I could quit that and restart just to show you just how quickly we can get this thing loaded. So there we were running a start script. Again, RDFox comes with a very powerful command line interface, but also allows you to run everything via a script. If I just walk you through that very briefly, we've got some setup that's going on at the top. We have some import statements. We're importing the data and some decoration that's used on the website and the rules. I'll show you those rules in a second. And we're also then issuing a few select statements just to check that the system's set up as we expect it to. And finally, we configure our endpoint and start the endpoint. The endpoint enables the REST interface to RDFox. And this is how RDFox is being queried by our end application. Okay, so here's a sample of our compatibility rules. Here I'm showing again the one we illustrated in the presentation. This rule determines compatibility between a DC motor and its power supply. All fairly straightforward. The way to read data log is to look for this :- symbol. And you then think about the left-hand side that precedes that symbol and the right-hand side that follows it. If I start with what follows it, so the right-hand side, we have all of the pattern, if you like, the pattern, the body of the rule that's going to be matched for this particular rule. Another thing to look out for are these question mark letters or question mark variables. The question mark denotes a variable within the language we're using here, which is data log. So our variable M is a DC motor, is how to read that first line in blue. Our variable PS is our power supply. So that's just fixing the types of those two variables to what's in the system. And then we look at some properties of those systems. So PS provides a DC voltage, that's fixed. PS provided voltage, we give that a new variable PV, provided voltage. PS provides a current, PC, again, a new variable. And then we think about the requirements of the motor. So the motor requires a DC voltage. Our motor's required voltage, RV, and our motor's required current, RC. And now we have a filter statement to run. So we want, if you remember, our voltages to equate, to be equal. And we'd like our current, the current supplied, provided current, to be greater than or equal to the required current. So that's everything we need to establish a rule of compatibility between a DC motor and a power supply. Let's have a quick look at some of the other rules within our system. As I said, we're using data log here, and we can see a number of different rules that are established. Here is the one for our motors with their power supplies, and we've got a similar one here for the power supply to its switch. We have variations on the motor theme for stepper motors, and so on and so on. Again, each of these rules can be thought of in isolation within the system, and when you're thinking about those rules, you're thinking about the two halves that establish compatibility. So individually, each are fairly straightforward to write. Okay, so that establishes compatibility. So let's have a look at a query to do with compatibility, and then we'll follow on with a query that's used in the final solution where we're looking for configurations itself. So rather than look through the configuration demo page, what I'm going to use is a Sparkle editor that ships with RDFox. And into here we can write the query language for RDFox. We use our standard Sparkle syntax for our querying. And I can run queries like this. And this is a fairly simple one to read, but let me read it for you. We have a variable s where we're looking for compatible with relationships with an O, a variable O. So subject is compatible with an O object. And when we find one of these compatibilities, the other thing we're matching on is the name of the subject and the name of the component that it's compatible with. And we're going to output. So the output of our select statement are going to be the initial component's name and the compatible name. And we can run that query to see a bunch of answers. There are many compatibilities with our system, and RDFox, the query UI here, shows us the first 200 answers. And we see we're incredibly fast. So those answers were returned in 52 milliseconds. We can see DC motors compatible with DC supplies, stepper motors compatible with stepper controllers, and so on and so on. So there's a query that just shows you an example bit of Sparkle, extracting compatibilities and their names. Now let's have a look at a query that does the full gamut and explores rotating solutions. This is a little bit more involved, so I won't go into the details of this, but what you see towards the end is there's a filter condition specified, and the filtering here is looking for a particular torque, particular speed, and then returning all of the components associated with that. So we run the query. We can see for these particular constraints, there are exactly 47 possible configurations, and those are returned again well within a second, just under 700 milliseconds, and we see the full set of both the output torque and speed plus the cost, along with all of the individual components that make up that configuration, and an identifier for that overall solution as well. Okay, finally, end back at the place where we started. So here is the configuration app that we constructed, and now I can go into a bit of detail as to what's actually going on under the system. So if I reverse it back to our starting point, we can see things getting updated as we go. So every time a change is made to one of these entry fields, Sparkle queries are running off left, right, and center, querying the database, and, for example, finding out the overall number of solutions available with the criteria. So what does this tell us? This particular thing tells us there are over 48,000 possible solutions in our system because we haven't really specified any criteria. As we start typing in the constraints that we're after, so a speed of 800, for example, torque of 2000, we can see everything being refreshed in real time, and we can see our results starting to be constrained by those parameters. So those Sparkle query, in fact, that second Sparkle query I showed you, is being fired off with those filter parameters being changed as we go. And what we might like to do is say, okay, we're closing in on our solution. Let's specify a cost and constrain our cost to something that we can see is possible. So $102 as a constraint. And there you have all of the possible configurations available for those particular constraints. The final thing I wanted to show you was just highlight the incremental features of RDFox. In fact, when I was showing this to a client, they said, what if we had a new component that we wanted to add to the system? How would that work? And for fun, they said, for example, let's say someone came up with a completely new type of motor. Maybe it's a windmill of some sort. So no problem. Here is our windmill, and we can import windmill.ttl into our system. We haven't yet established any compatibility rules for windmill, so let's write those. We're essentially saying a windmill is compatible with wind, and a windmill is a form of rotating solution and can participate in the rest. So I've imported the data. Let me now import our rules, windmill.dlog. And now if we go through our system, we should start to see windmills start appearing in our solutions. And we're saying windmills are very powerful things just so they stand out from the crowd. And if we raise our constraints, we can see some of those start to filter in. In fact, here we go. Here is the only solution with this particular criteria, and it contains a windmill. There you go. So incremental reasoning in action. We have just live included a new component. We've included new rules to the system. There were over 48,000 possible configurations. There were just over 500,000 triples, data points within our system. And yet we've added this new component, this windmill, without noticing. Incrementally, the rules were added, all of the compatibilities fired, and we have a new configuration already live within our system. So that concludes the show for today. And in summary, RDFox has gone through, computed all those compatibilities. In fact, you saw that because I restarted the system live during this recording. Reasoning happens in memory and incrementally. We demonstrated that with the addition of this fictional windmill component. We've shown you RDFox rules and how they can encapsulate the logic of compatibility and the overall rotating solutions. And we've got absolute flexibility of how we model that data to make sure we end up with a flexible and consistent and most importantly correct system in the end. I hope you've enjoyed this video. Please tune in for more.